you remember the 0th law of thermodynamics?
Yeah, it's like if 1 is even with 2 and 2 is even with 3, 1 and 3 are equal.
Yep. So yeah, if 1 and 2 are in equilibrium, 2 and 3 are in equilibrium, therefore 1 and 3 have to be. Yep. Very basic, and we'll do all these because it kind of covers it. What was the general form of the first law? We'll break it down further next, but what is the first law? What is that really? Yep. So that means the change in energy of the system is equal to some energy in minus some energy out. Okay. And when we deal with this, what do you have to identify? What do they mean by in and out of what? Through the boundary. Yes, it's a boundary. You have to define a boundary, okay, which is a dotted section. Whatever enters or exits that is the right side of that equation. Good. And the second law, what was the second law? And really, what's the purpose of the second law? Remember? It tells direction of heat. We'll get to this, but you don't have to know it now. Sure, I'll just do it like this. I'll just say general form. So we'll cover this probably 10 weeks down the road. But this right here is the general equation of the second law. And that's the validation to say, okay, it goes in one direction. But don't worry about that. Just remember, okay, it tells you the direction. Always good to remember open versus closed systems. Closed systems are easier because they have no what entering through the boundaries. No what?
Mass.
Of a fluid, yes, yep. There's no fluid energy coming in and out of the boundary, yep. Okay, I will not give you that on the test. It'll be a closed system, okay? I'll give you something to do with a closed system, all right? Okay, good. What do I want to do? Actually, let's do this first. So let's look at more of the first law. So let's break that down. And I have practice. We're going to do some old test questions too. So delta E of the system equals E in minus E out. And let's write all of this on the left. So we have delta KE plus delta PE plus delta U equals Q net plus W net plus E of the fluid net. So I just abbreviated that, which is fine. So these nets it's just an in minus an out. Okay? So if I give you one of these problems, if it deals with the first law, I want you to write in your solution, write first law, and then write this whole thing down. Then we can cancel stuff, right? Okay? That's what I want you to show me, that you know exactly what you're doing for that. So if we look at the left side of this equation, delta KE, that is kinetic energy of the system. Okay, but if it's a stationary system, that goes away. So this room is not moving, so that term would go away. The delta PE, it's not really changing height, even though, yeah, we don't do that in this case, okay? So that goes away. But the room could change its internal energy. Inside the room, the temperature could change. Over here, we could have heat coming through the boundary. We could have work. We could plug in an electric heater. We could plug in whatever. Okay, that's electric power. And we could somehow magically drill a little hole, seal it off, but put a shaft in here with a fan, right? So then you have shaft energy coming in. So we have heat, we have mechanical object as work, and we could open the door eventually and have fluid coming in. But that you would cross off immediately because you're going to assume it's a closed system. Okay? Does that make sense? Question on that. So the other thing I want to point out is we talked about this fluid energy. And if we open that door, that fluid can come in at a speed. It could come in, maybe we open up one of these somehow and the air comes in there, so it has a different height. It could come in at a different temperature or whatever, okay? So this, we kind of quickly talked about it as mechanical energy. Do you remember that? The little EMEC, which is little ke plus PE plus P over rho. And I'm going to add something. Just to make sure it's making sense to you. And actually, that's fine. I'll just make a note of it. We'll make a note. So this total fluid energy at state 1, say we open the door, that fluid could have kinetic, could have potential, it could have pressure work, which is flow work, but it also could have a temperature, an internal. But when we deal with mechanical energy, we ignore that. Okay? So this right here is mechanical energy because it ignores heat, which is really, if you had fluids or taking fluids, you'll learn this. This is Bernoulli's. That's the Bernoulli's equation. Okay? But that's fine. As long as you understand mechanical energy of a fluid. This is mechanical energy. It's only of a fluid. And then how do we get power from this? W dot from if we have this little EMEC. Have to multiply it by divide by time to get power, but times a flow rate. So mass flow rate. Okay. So in reality, yeah, I'm not going to test you on, if I give you this first law equation, on it's going to be a closed system. But technically, this term we have dealt with, and I could give you, I'll specifically say, okay, using mechanical energy, remember with the water going down a dam at 90 meters or whatever, we've done those problems. Those really could go back into here, and you can expand that first law even more. But for this first test, you're going to ignore this if you do this closed system and just focus on the mechanical energy aspect of that. Okay? Because the next section I'm going to talk about is we use this in pumps, turbines, fans, whatever, as a combination to find what? Efficiencies. Okay? So we also dealt with efficiency, which was eta, and that's your output over the input. So let me go to this document and show you. So I just posted this on Blackboard. It's 1 page front and back. I'll make copies when I go back if you want to grab one later, or you can just download it and print it off. You can use this on the exam, all right? So here, it just goes through energy, mechanical energy of a fluid. So look, no heat, and includes flow work, which is pressure over density. And I gave you big units and small units. What's the difference? What do these small ones mean? Specific variables. Yep, they're per unit mass. Okay. This is, I just give you the change in mechanical from 2 points. Down here, I give you this E dot mechanical. This right here is really what? Power, too. Okay. Then I gave you equations for work. All right, and work is the integral of f dx. And I'm going to talk about a little bit in a minute more about this. Okay. Heat, which is, again, the integral of q dot times dt. Okay. Then, here is the first law that we just talked about. This is in what units now? So it's the same as up here, but I divided each term by delta t. So it's basically kind of like a power or a rate term. Yep. Okay. These two over here, if I can zoom in, are just other mechanical energy notes that you want to remember, okay, from up here. And then finally, I give you the efficiencies that we talked about for a pump, a turbine, a motor, and a generator, okay? And actually, a lot of this stuff is taken right out of the review section in the back of that chapter, chapter 2, I think, maybe, of Senegal, okay? So this is taken right out of there and some of those other equations, okay? Questions on that general aspect? Okay, the last thing I'm going to talk about, then we'll do some practice problems. Come on, now you're stuck. There. Is, say I gave you X and F. So say I gave you X and I gave you F, and I say plot a graph for me. What would I expect on the graph? Title. Yep. So no right title, right? An actual title.
You don't like versus titles?
No, you can. So like over here, you would have force, and down here, whoops, you would have X in meters. On a good title could be force versus position for a piston cylinder device. So be specific. So yeah, this is acceptable, Joe. Or you can say force as a function of position for blah, blah, blah. So we got a title, we got labels with units, and then we'll get something like this, right? And you can do a linear fit or whatever, it doesn't matter on this, okay? Now, if I say part B, show me graphically how to find work. Anybody know how to do that? Yeah, so there's an equation that you could use, which we know that work is what? Integral of f dx. And we know integrals are just area under the curve. Yep. Okay. So, or you could find the equation of a line, right? Like y equals mx plus b. So it'd be m times x plus b. So let's pick something. I don't know. Let's pick 2x plus, I'm picking something random, negative 10. Say I wanted to integrate that. So if we integrate that, what's the first term become? Yep, you guys do it ahead of time. Oops, I like to do it long just because. And then minus 10x. And that's evaluated from xf and x naught. Now I won't have you do an integral. I won't do that. Just because it's fine. I'm not testing on that. I just want to make sure you understood, okay, if I give you a linear line, how to find work? It's just the area under that curve, okay? But the area, which is the blue, and you plug these values in, you're going to get the same answer. It works, okay? All right, questions? All right, let's get some practice problems out here. Okay. Exams. This doesn't say, so let's just pick one. See what we had last year. Fantasy accelerate. Okay, try number 1. I'll give you a few minutes, and then we'll go over it. So always remember, anytime you see fan, pump, turbine, those all use some sort of fluid, right? So right now, always think, okay, we're going to use the mechanical energy equations that we've been taught. Don't worry about anything with the first law for that. Always remember, okay, let's look at mechanical energy and efficiencies equations. So, and technically, the equation I'm going to show you here in a second, you could get if you use the first law, but don't worry about it. So, in order to find power, what did I tell you that equation was? EMAC, yep. So what's the equation for mass flow rate if you're given those two at the top? Yep, yep. And then what's inside EMAC? Yep, yep. 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 How did I write it here? Hold on. Yep. So I did it like this. Technically, hold on. I'm going to do something. I'm going to fix it. Change this to delta EMAC. So we'll do V2 squared over 2 plus GZ2 plus P1 over rho. And then we'll subtract V1 squared over 2 plus GZ1 plus, oh, that should have been a P2, right? Sorry about that. P1 over rho. And what can we cancel? Elevations. Pressure, we're going to assume they're atmospheric. I didn't give you anything with that. And V1. Yep. So W dot becomes 1.15 times 0, or times the, I'll put the unit in here. It's 3 meters cubed per second times 12 meters per second over 2, and that's squared. So 248 watts, is that what people got?
And then you canceled pressure over density.
Yeah, we're going to assume pressures are the same at the 2 points.
We're
Yep.
also assuming the same thing, correct?
Yep, same height. Yep. So technically, here's your fan, and here's the blades. So this is 0.2, this is 0.1, and the air is shooting that way. Yep.
No.
Yeah. Go ahead, whoever. Cameron.
Alright, so I was gonna ask, so for the test, would you want us to draw small sketches like that? Would that be important for you?
You can, but if I ask you for short answer, you don't have to. As long as you give me an equation, and then you plug the numbers in the box, that's all I'm looking for short answer. Yep. Okay. So that, hopefully, 5 minutes. That's what for short answer, 5 to 10 minutes. And then, depending on how the engineering problem goes, that could be maybe 20 minutes, 25 minutes for you to think about, okay, how do I do this, all right? So question on this one. So there's gonna be probably a couple short answer like this, like, okay, here's a quick thing, plug your number in and give me it. All right? So for the engineering one, I'll give you 5 minutes to try to set this one up. So you have 4 kilograms of a certain gas is contained with a horizontal piston cylinder assembly. The piston cylinder is fitted with an electric resistor, and when turned on has a voltage of 100 volts and a current of 150 amps. It is turned on during expansion, which takes 10 seconds. The expansion creates a value of work equal to 17 kilojoules. The change in specific internal energy, U2 minus U1, is negative 5 kilojoules per kilogram. There are no significant change in kinetic or potential, and determine the net heat transfer for the process. So, if you're reading this and you're like, oh my God, where do I start? Always write your givens, write your find, do your sketch, label what's coming in and going out. Then in your solution, we know we're dealing with energies, conservation of energy, just write that whole equation out. And then stop and pause and think about it. So do that, okay? So the when you draw your piston, draw it like this. Okay. All right. I should have provided the sketch, but that's how I want that. Okay. You could have done it the other way. It wouldn't have mattered really. I mean, it doesn't matter. So. All right. Let's go through this. So, if I'm reading through this, first thing I want to do too is find some keywords or underline some keywords. First 2 words are key, right? 4 kilograms. What does that mean? That means that's the mass. You'd be surprised how many actually people forgot that on the test. A lot of people, because it was like the first 2 words, right? Sometimes they, yeah.
It's not a number, so it
Yep.
doesn't stick out.
Yep. Yep. So we have a piston cylinder device. Okay, so we can make a sketch. The piston is fitted with an electric resistor. Oh, okay. So we typically, this is our boundary, and we have some sort of resistor in here. Okay. And I'm going to identify that as work in, because it's a mechanical aspect. And when you turn it on, it's going to heat. it's going to supply power in, okay? Okay, so we have a voltage of 100 volts and a current of 150 amps. Okay, those are important, right? Because that gives you what? Power of this electric heater. Okay, good. All right, so this is turned on during an expansion. Okay, so this thing is going upward. So I'm just going to put that right there. And I'm going to say delta T, 10 seconds. Another keyword, 10 seconds. Okay. Then it says this expansion creates a value of work equal to 17 kilojoules. So it expands out, so we'll assume it's outward, and we'll call that boundary work. Now, I actually made, that was an extra if people understood that. So I didn't mark off if you didn't have that in the test. Okay, it was like an extra bonus point. But it expands outward. Okay, so we know there's something to do with that. Then it says the change in specific, specific internal energy, U2 minus U1, negative 5 kilojoules per kilogram. Okay, so delta U, negative 5 kilojoules per kilogram. 5. For mass?
Yeah, so can you multiply that?
That would be sure. If you want to put that in your givens, sure. That would be m times little u, delta u, right?
Yeah.
That would be 4 kilogram. I'm okay if you do that here. So negative 20 kilojoules. Is that what you said?
Yeah.
Yep. Sure. That's big U, delta U.
Yep.
Underline that. So there is no specific change in kinetic or potential. Okay, we kind of already knew that. And we're finding the net heat transfer. Okay, so there's some sort of heat, and I'm just going to assume outward. Okay? And I'm going to make it, I don't know, let's call it out. Sure. Q out. If you find that you get a negative, then you know it's what? The opposite. It's actually coming in, okay? So we're going to find Q out. It could be Q in. We don't know. So if we get negative, then we know. But we've identified key variables. We made a sketch to the best of our knowledge. We've written everything. Then our next step is to write first law and write that whole thing out. And let's start with the, doesn't matter, whatever one we want to start out with. So Q in minus Q out plus W in minus W out plus the fluid in minus the fluid out. Now, assumptions. We forgot those, but you can start writing those now, right? We're going to assume it's a closed system. So that makes those two are going to be gone automatically. Boom. It said in the problem, ignore these. We kind of already knew that. All right. And, we already have big delta U. So we kind of figured that out from the givens and units. So that's good. Okay, we have a number. On our sketch, did we have Q in?
Yeah.
Not based on the sketch I drew. You could have if you wanted to, but there is none. So I just said, okay, based on my assumption, there's no Q in. And we said there was a Q out. That's kind of what we're looking for. We had electric in, and we had this boundary work out. Okay. So I'm going to rearrange and solve for Q out. So W in minus W out and minus delta U.
No, it'd be minus W in plus W out.
I brought Q out to the left side.
Yeah.
So then it's in minus out minus W.
Yep.
Yep. Yep. Now, I'm okay if you notice here, I didn't put dots on these. You'll get to that here coming up, okay. As long as you labeled arrows, you can then figure that out later. So let's scroll down here.
In this sketch, what's the dotted line around the inside?
The boundary. So that's what is coming in and going out of the boundary, okay? Yep. Good questions. So Q out equals, all right. So the work coming in, we know is electrical. So what is that equation? Yep, voltage times I times delta T. That gives you what? W and not W dot. So that's one thing that I was looking for on this test. Did you understand that you had to use energy or energy per unit time? Minus WB, that's a number, right? And then minus, what was that, negative 20 kilojoules. Make sure it's minus a negative, because the negative is important. And I don't know why I put that number in there, but you can. So always remember that this is work. If you did it the other way and you did rates, what would you have to do? Want me to give you, want me to show you this alternative equation that you could have used? Oops, no. Make sure I do this right. Right? Divide the other terms by delta T. Yes? Plug my, oh, is it going to die? How many? 10%. I think we can do it. Thank you, though. We're almost there anyway. So you could use this one or that one. Doesn't matter, right?
Right.
But they're all the units are the same. So I'm just going to use this one. Q out. Voltage was what again? 100 volts times 150 amps times 10 seconds. Okay, minus, was that 17,000 joules.
Can we convert the kilojoules to kilojoules?
Sure, you can do that. Yep, I just do it the other way. And then minus, or actually plus what? 20,000 joules? And can someone put that in their calculator real quick? Yeah, that's what I was getting. Yep, positive?
Yeah.
Yep.
Holy crap, what does that mean? Energy's going out. So our direction was right. It was correct. Good. Yep, it's outward. It's going outward to the surroundings. Yep.